Okay, this is class 3 that we're going through right now. And the main thing about what we're going to do in class 3 is we're going to spend a little bit of time reviewing what we did last time, and then we're going to dig into our first C language programs. And then that's going to lead to a lab, not this class, but the following class. So let's go ahead and get started here. All right, so the first thing is, here's what we're going to cover today. We're going to review I'm going to prove to you that vision of how the computer works was accurate, which is going to give us kind of a low-level view of how the computer functions at an architectural level. And then we're going to look at the C language compiling process and look at our first kind of C language program. All right, so let's go and get started. So to review how the computer works, I typed how the computer works into Google and did an image search and came up with these two things, which were kind of like that stupid diagram that we talked about, where it basically says, well, you've got some input, you've got some output, you've got some processing, and you got some storage. And then here's kind of that same 4-box diagram on another thing where the arrows don't even match up quite right, but it's the same kind of thing. We have input, output, processing, and then some sort of storage component. But as we learned, those diagrams are, well, not technically wrong. They also aren't really useful. They're kind of a dumb diagram that has no functional purpose other than to kind of show this really super generic thing that you could apply to anything. How does a goat work? Put grass in, poop comes out, does goat things inside it. That's essentially what these diagrams are. How does a car work? You put gasoline in, and it does some car things inside of it, and it moves around. So you could apply a diagram like this to anything. So they're completely pointless. So here are some other diagrams for how a computer works that I found when I did that same search. And this one, well, at the top you have a computer, and then it's got some hardware and software and some input, which makes it look like the input and the software are kind of equivalent to hardware. These diagrams, and this one over here says like output devices, operating system, CPU. So somehow the user puts things into the input devices, which somehow they connect to the operating system, which then the operating system connects to the CPU, which connects back to the operating system, which connects to the output devices. This is all completely wrong too. So these are actually worse than the other ones. These are even more wrong. So let's go to our diagram for how the computer really works, and then I'm going to prove to you that that's the way it functions. So here was our diagram that we had come up with in class. So we have memory, which are really just a collection of circuits, machines, devices, whatever you want to think of them as, that store numbers. And really those numbers are just stored as binary bit patterns or switches that are on or off, and 8 switches per memory box, so 8 switches per byte. So you can store a number in the range of 0 to 255 in these. And here's the CPU, which connects via these wires that are called the system buses. It connects via the wires to the memory boxes, so the CPU can kind of go out and request the contents of a memory box. The little latch will open up. The switch pattern will flow out onto the wires. The CPU will then open a gate into one of the registers to allow that number to flow into the CPU. So in other words, this pattern 100 that the keyboard happens to be connected to here, the CPU will go to that address, open up that box, the pattern 100 will flow out on here and into a register, and then we would have that value in memory in the CPU's internal memory called registers. And the CPU also has a collection of circuits that can do simple instructions like move, which allows us to pick up something from memory or copy the pattern from memory into the CPU, or move, copy from the CPU back to memory. And then simple arithmetic operations like you'd be used to doing. Okay, and then the only other part of this, besides the processor, the system buses, and the memory, are the I/O devices, which really just show up as special circuits that interface to those devices. So for example, the GPU connects to some region in memory or boxes in memory that when the CPU puts values in there, stuff shows up on the screen. The keyboard, when you type on it, it puts numbers into a box in memory that the CPU can then go and move the data out of, and then it can have the pattern of whatever that's associated with a key on the keyboard. Same thing with mouse, same thing with hard drives, same thing with any I/O. So in other words, it doesn't work anything like any of this junk that's over here. It works exactly like this. And the cool thing is every computer system is some version of this. Okay, now moving on. And notice that that's simple. Like here's a little example of some CPU instructions. Move from address 10 into register A, which will be getting something from the keyboard into register A. And then the next line, moving something from A to register or to memory location or address 11, which would make that show up on the screen. So you press an A on the keyboard, this number would change. In order for that to show up on the screen, the CPU would have to go to that memory box, move it into the CPU, move it back out, and then the A would show up on the monitor. All right, so very simple. Okay, so there are those components that we talked about. We had memory, we got the CPU, we've got registers, we've got the system buses, and we've got that I/O memory that's kind of the special memory that interfaces to devices. And we already looked at what that looked like. So I want to prove to you that that's really how the computer works. So we're going to take a little bit of time here to do that. And I'm going to take a look at a simple program here. We're going to execute that program and see what it does. And then we're going to try to look at the CPU instructions of that program. So we're going to kind of, and this isn't a lot of what we're going to be doing in the class, but it's going to be helpful for us to know how the CPU works, how memory works, how the CPU instructions interact with that memory, because again, this is a systems programming class that's going to be important to us. So let me quickly switch here to the display, and let me start a command interpreter here. We're going to take a look at that program quickly. Okay, so you'll notice on the screen right now, I've got this kind of command interpreter. And let me see if I can make that font bigger on that. And maybe you can see that a little better now. All right, so what I have on here is I've got a program called hello.exe. So I'm going to run that program by just typing hello, and you'll notice that all it does is say hello world exclamation mark. That's all that that program does. It's a very simple program. It just prints that thing out on the screen. Now, what I want to do though is like that hello.exe, how does that actually get loaded into memory and then cause that to run? So what I'm going to do is I'm going to use this program called File Insight, which is actually a free tool you can download from McAfee's website. There are other tools like this as well. There are a number of them. There's one called OdaWeb, which is a web-based program. There's one called IDA Pro. There's a free version of that you can download. But this is something that's free. And let me adjust this so we can actually see all of it on the screen in a window here. So I'm going to move that up there. And let me bring this down here. Okay, so now I'm not covering any of it by my picture there. Actually, let me move it over to there. Okay, so now you can kind of see that. Actually, I probably could bring this over a little bit to there. All right, so now you can see that program. So what I'm going to do with this File Insight program, what this program does is it lets me look through kind of the contents of a file and inspect it in some way. So I'm going to do a file open on this, and I'm just going to open that hello.exe, that same one we just ran. And the first thing you'll notice is that there's this window up here that has a list of kind of different labeled things. And then over here on the right-hand side, you'll see this thing full of numbers. Now, what this is the actual contents of that file. And you'll notice that that file starts out with at offset 0. So this isn't the actual memory address. This is kind of the offset from the beginning of that file. And then if you look down through this, you can see these numbers increasing. So that's 0, all zeros, that's 1 0, that's 2 0. What these are, these increasing numbers, you might guess, is that would be the addresses of each of these values that are in memory. So in other words, this is offset 0 is this 4D, which is just a hex number. That's just the contents of 1 byte of memory there. And then after that is 5A and 90 and 00 and so forth. So you'll notice that those increase. So if we count these, there's 16 of those because 0 are offset 0, offset 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And then we're to 1 0. 1 0, 1 1. 1 2, 1 3, all the way up to 1F, and then 2 0, and so forth. So in other words, this is just showing me the bytes of memory. When this hello.exe gets loaded into memory, this is what will be in there in that order. Now, this little pane down here, if you click on the Disassembly tab, it's showing you how or what this part of the program is interpreted as in assembly. So the thing to notice over here is if you look down here where it says 4D, 4D is this instruction. DEC, which is a form of subtraction. EBP, which is a special register. That's the extended base pointer. But that's just a register in the processor. So what this is saying is subtract that, or 1 from that register. The next instruction is 5A. And notice that that's showing that instructions are just coded things. Now, the thing that interests me, though, is notice up here we have this thing that says entry point. The entry point is kind of where the program begins execution. So if I click on that, it'll take me to that. And you can kind of see what that code looks like. So the first thing that happens is the subtraction, and then a move happens, and a call, which is a special kind of a combination instruction that's a special kind of move that jumps in the code or in the program where it gets the next instruction from. When it comes back from that, it then calls another one. When it comes back from that, it does this special kind of move, which LEA is load effective address. Then a subtraction and a move, and calls, which are a kind of move, and load effective address, which are a kind of move. But you'll notice as you scroll down through here that it's really just those things that we're talking about. But from the computer's point of view, this sub ESP 0x1C, that first instruction, notice to the computer that doesn't look like sub. It looks like this. 83 EC1C is how the processor sees this instruction. So all of these, the only thing that's in memory are these numbers that we see over here. So in memory, it looks like this over here. It's not even broken up by here's one instruction, here's the next instruction. It's just a bunch of bytes running through memory, some of which are instructions, like the 83 EC, and some of them are data for those instructions, like the 1C. And so this over here is kind of how the processor is interpreting that, but in memory it just looks like this. Now, one of the things that I want to do with this program, though, is let's actually kind of scroll through this, and you'll notice it a lot where it looks like kind of garbage like we see over here. Okay, so this pane over here, these are the addresses. This is the byte version of that. In other words, the numeric values in hex that are stored in memory. And over here is what that looks like in ASCII if we were to look at that and using the character code for it. So in other words, this is all just contents of memory that are in this file. And if we look through that, we can see a lot of it looks like junk. That's just program code stuff. But if we just keep searching through this, we'll eventually find something where it doesn't look like junk anymore. Now, down here, here's where we get some stuff that looks like readable text over here looking at it there. So really in memory, there's our hello world, HELLO world, right there. And if you'll notice, that starts right over in, if you, for example, if I click on this H, you'll notice that that's address 1424. So 0, 1, 2, 3, 4. That's that 48 is the H. And then the 6, 5 is the E. And then the L, or 6C is L, 6C is L, 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 O, 20 is space, and then we have WORLD exclamation mark, and then at the end of that we have this 0, which is signifying the end of that string. So the cool thing about this is the computer doesn't know it's saying hello world, it's just copying data out of that portion of memory. So to show that really how fragile this whole thing is I could actually just change some of these values in memory. So let's do that. So over here, here's the H, that's the E. Let's change the E to an I. So notice 65 here is an E. So let's put a 66 in there and see what we get. 66, now it's an F. So 67 is a G. 68 is an H. So 69 is an I. So we've changed that H to an I. Now it says hello world in memory there. And now let's move on to this next thing here. There's a L and an L. Let's change that to a P. So L is 6C. So how many do we have to go ahead to get to a P? L to M to N to O to P. So we need to be 4 ahead of 6C. So 6C, D, E, F. So 6F, 70. So let's put a 70 there and see what we get. And now you'll notice that that has changed that to a P over there in the text version of that. Let's change this one to 70 also. So 70. And now our string in memory says hippo world instead of hello world, which hippo world sounds pretty awesome to me. But now that I've changed that, let's go ahead and save this program. So I'm going to go and do a save. So I've saved that. So before I do anything else, let me minimize this and go back to the screen. So you'll notice here where we ran it previously, we said hello, and it just said hello world. Let's run that again. Hello. And now it says hippo world. So notice the CPU just loaded that thing into memory, followed those instructions, did what it said, and it said go to this place in memory and copy these characters out onto the screen. It doesn't know what the characters are, doesn't know that we modified it, knows nothing about what we did. It just blindly follows what the instructions say. And in our case now, we made a program go from saying hello world to saying hippo world. So very much exactly like the way that we described that processor is working. Very simple system that all we really did was copy the data out of one part of memory out to the screen, and there you can see it actually happening. Now, you might have noticed like there were a whole bunch of other instructions around there that are doing subtractions and loading addresses of things. A lot of that is stuff that is, when it compiles that program, the active part of that could actually be much smaller. But when we compiled that and built that into an exe, it has some stuff in there for Windows to understand how the thing gets loaded. It's got some library functions in there that are built into it. But anyway, notice that we very simply changed that. Now, let's take a look at one other example here of a program. And let's look at this rather than just changing what shows up on the screen when we run it. Let's change it so it changes the behavior of that program in some way. So in other words, here, looking back at this thing, remember some of these things, like let me go back to the entry point here. Some of those things are instructions like we see down here. We could actually not just change the data, like hello world to hippo world, but we could change the values of this to make different instructions here. And that's kind of why computer systems security can be difficult, is because if you can change the values in memory in some way, then you can change the instructions that determine what the CPU actually does. And that's why computer security things for you download some malware onto your machine and suddenly it takes control of things. That's the kind of thing that if you can get access to memory and changing it, then you can make the CPU do things that were not originally intended. And notice that, again, the CPU is not a brain, it's not smart. When it loads up, it just goes to this address and it blindly runs whatever instructions are there as coded by these numbers. So if I could change a number, I can change the instructions. So let's look at another program. So I'm going to go to, let me go back to here. So I'm going to run another program here. This one is password.exe. So I'm going to run that. And notice what it says. This is the presidential lunch code password safe. So it's asking me to enter a password. And I don't know what the password is. That's supposed to be a secret. But I could try some here. I could try to brute force this and say, let me in. Well, that didn't work. It said, nope, go back to where you came from. So I could try a different one. I could try like, let me in, please. Nope, that didn't work. But knowing how computers work, that if this thing has a password and it's checking to see if I got that password right or wrong, somewhere in the code has to be something that is checking the password and comparing it against some password that it knows. And then it has to make a decision of, meaning perform a comparison to either say yes, let them in, or no, keep them out. So that has to be in the code somewhere. In other words, there have to be instructions in the program that are deciding whether to allow access or disallow access. And if I can find that part of the program where that's happening, where that comparison happens, then I could get rid of the comparison altogether and always allow them in, or I could change the comparison so that it, or I could find the thing it's being compared with and compare it with something else. And so since the CPU doesn't know what it's doing, it just says, hey, I found this instruction 83, I take this action. I found this instruction C7, and these things take this action. I found this instruction FF15, F8, take this action, or FF15, I guess. So whenever it finds those instructions, it just makes it take an action. So what I'm going to do is I'm going to, before I do anything else, I'm going to go and do a open of that password program. All right, so there's password.exe. And you'll notice that it kind of starts in a similar way. It's got similar stuff in it to the previous program. You'll notice up here, it starts with a subtraction just like the other one did. It does some other stuff here. A lot of that is kind of setup stuff. But then it also is doing some other things down through here that you might scroll down and look through. And you could scroll through a lot of the memory. And one of the things to notice over here is notice that we've got these different sections. There's the text section, there's a data section, there's an R data section. And essentially what these different sections are is that the executable is divided up into different blocks that get loaded into memory in different ways. So text, the .text section over here, that's where the code actually lives, the executable code. The data section, the .data section, is where variables that are going to have their values modified or changed live. And the R data is kind of a section that is storing data that is not typically going to be changed. In other words, like that string hello world would be in the R data section. So one of the things that I could do if I really wanted to figure out this program is I could find the code that checks the password and change it, or I'm just going to click on this R data section, which is where kind of string constants and things like that are. And you'll notice here it has highlighted that section. And you'll notice that looking at this, presidential lunch code password safe, enter password. And then there's this string here, fake news with a Z 420. Now that's something that didn't show up in a printout and it looks kind of suspicious. So I'm going to say, well, that might be the actual password. The password could be hard-coded in here in this program and stuck right there. Now, if the person who wrote this program was clever, they may have encrypted that password in some way when they stuck it in there. But now notice that the password itself, or fake news 420, is just sitting in there, right there in the executable. So let's, before we edit the code and make it do something different, let me go and run this again, and let's see if that actually works. So let's run the password program. And with password we read out of there was fake news with a Z 420. It would have taken me a long time to guess that. And notice now it gave me the launch code, or it's supposed to be the lunch code, I guess. And it just showed me what the lunch code was. Notice that the launch code was actually in that our data section as well. So taking a look at that quickly, you notice that was in there. Grabby McGrabber hands with a Z is in there. Also the messages to say no, or go back to where you came from or whatever, all that's in there. And there's some error messages and things in here as well. You'll notice it's all just sitting in memory, because that's the only way the processor can do something is with code that's in memory, meaning instructions that are in memory, and data that's in memory. And one of the pieces of data in this program is the password. And to get into the code, and one of them is the code itself that it sends back to you. And then we have the prompts and the error messages and everything else in memory as well. So this is that picture we had of how the computer works is exactly how it works. A bunch of bytes of memory, a CPU that gets its instructions from that memory and carries out those instructions, like these over here. And the data for those instructions is in memory, the data that those instructions refer to print things out and show prompts and compare things are in memory. Everything, all of the data is in memory, and the processor just gets its instructions that then pull things in from memory and do things with it. Okay, now with this program though, what if I wanted to make it so that I changed its behavior? I changed the actual program, not just looked at the data and did something. So right there, I kind of inspected that executable. I found out what the password was, and I used the password to get into it without changing it at all. But let's say we get tired of typing that same password. We want to make it so when I run it, I don't have to have the right password. I can just run it without the password. So how can I figure that out? So what I'm going to do is I'm going to quickly use a different tool here to inspect that. And this tool is actually called OdaWeb, which let me go bring this over here. So I typed in OdaWeb, and the first link here, this ODA, that's an online disassembly. And what this is, this tool, I don't even have to install anything on my machine to use this. Let me make this fit the screen a little better here. Probably right about there's good. But this tool allows me to do kind of what I was doing in that File Insight program, but I can do it without installing anything on the machine. If you can get to a web page, you could use this tool. So watch what I'm going to do. I'm going to say File. I'm going to say Upload File. I'm going to choose File, and I'm going to upload that password.exe. That's the one I want to look at. I'll say OK. Say OK again. OK, and now that has loaded that. And again, in this kind of program here, you'll notice that there are things over on the side that are kind of labels for things that are in the executable. I'm going to click on _main because that's where the program is going to start. And you'll notice that this does that same kind of disassembly. Here's that 55 for push EBP. There's 89, do stuff there. But this is the actual code for the main function. And you'll notice that looking at that, there's some function calls. There's a putS, there's a printf, that those function calls up there are things that the compiler actually produced when this program was created. And one of the things that we're interested in this particular program is somewhere, if I'm typing in a string, and it's checking to see if that string matches the password or not, and then it decides whether or not to allow this to continue or not continue. In other words, let them into the program or keep them out. There has to be some kind of comparison there. And the place that that's happening in this program is, and I know this because I've done a lot of stuff like this and written a lot of programs and analyzed them, but notice looking down these instructions, if you're just looking at it in the way the computer looks at it, you could actually get a table, a book, and look up, okay, what instruction is 55? And you'd look up 55 hex, and that would say, well, that's push EBP. And I could go through memory and look all that up myself, but this program's kind of doing those lookups for me and putting the stuff in there. Well, one of the things that we know about the spot we're looking for is it's going to have some sort of a comparison of one string with another string. And I really don't have to look far looking down here. And I see something that stands out. There's a call to some other place in memory called strcmp. That's a string comparison function. And then when that call comes back, it does this test, which is a kind of comparison instruction, comparing EAX with EAX, which is basically essentially saying, is that thing 0 or is it not 0? And then the next thing that follows that is this jump not equal, JNE. That means that if this thing did not match, then we go one place, and if it did match, we go a different place. And you can see those two locations listed right there. And I could actually jump ahead to that address, that 401410, and that would be the place where it jumps when those things match. And it's a jump not equal. Well, one of the things that I notice is looking over here at the code, this 7555 followed by EB2D, that's the place where it's checking to say, hey, if the string was correct, I go here. If it was not correct, I go there, or vice versa. So what I could do with this program is let's just take this JNE 7555, and I'm going to go ahead and write that down quickly here so I don't forget it. So 7555 followed by EB2D. EB2D. I'm pretty sure that that has something to do with the comparison. And what I'm going to do is I'm going to change this from a jump not equal. I'm going to change that a little bit to a jump equal. So I'm going to go ahead and leave this O to web thing temporarily. And I'm going to load, or I already have password loaded here. So I need to find the part of the code that has that 7555. So I'm going to do a search, find. And I'm going to say 0x7555. And there it is. So 7555 EB2D. So I'm going to click on that space in memory. And you'll notice that there is the JNZ, which is the same as JNE, 7555, followed by EB2D. That's the place in memory that I'm concerned with. So what I'm going to do is I'm going to change that JNE or JNZ, which are really just, this JNZ or JNE is just a humanized version of that. They're really the same instruction. But that jump not equal, I'm going to change that so it's a jump equal. And I happen to know that the code for that is just one different than 7.5. So I'm going to change this to this part of memory to a 7.4. And now, once I've changed that and I disassemble that, now notice it's JZ instead of JNZ. So and notice that the difference between a 7.5, so if we think about that in binary, and I'm going to do this backwards for your benefit, 7 looks like this. So 0, 1, 1, 1. And then 5 looks like a 4 and a 2, or a 4 and a 1, I mean. So it looks like that in memory. So 0, 1, 1, 1, 0, 1, 0, 1. And we changed this to a 7.4, which is just that. So it's just one bit different that we made this 1 byte in memory in this program. And that's it. We made 1 bit worth of difference in this program to change the program. Now I'm going to save it. So I'm going to say file save. Click the save button. So now I've saved this program that used to require me to put in the password. So let's do it again. Password. And now I'm going to put in the correct password. Fake news with a Z 420. And now it's telling me no. Notice I got a different response from this program when I put in the correct password. It kept me out, which brings up an interesting question that since we reversed that comparison, what if I put in just garbage here? Now it lets me in. So I've changed this program that was password protected when you had and required you to have the right password by changing one single bit of memory. I've now changed it so that you don't need the password and it lets you in when you have the wrong password. In fact, it'll keep you out when you have the right password. And in fact, I could take out that comparison altogether and make it so it doesn't matter what password you have. I could just take out that whole instruction if I wanted to and make it go to the same place whether I answered it right or answered it wrong. And that would be really easy to do. So notice now I don't even have to put in a password. I can just hit enter and it'll let me in and it'll give me the information I want. And again, that's changing 1 byte. So the program, the code doesn't, all that the CPU has is a string of instructions. It doesn't know what they mean. It doesn't care about the security of them. It doesn't know what it's doing. It just says, I was told to load this thing into memory. I was told to compare this with this. I was told to, if it's 0, jump here. Otherwise, jump there. I was told if it's not 0, jump here. Otherwise, jump there. The CPU is just blindly doing those really simplistic instructions, one instruction at a time, and it's doing them as fast as it possibly can. So again, it works exactly the way that we described it in our model of how the computer worked. And the cool thing, like I said before, every computer system works like this. Now the instructions for what code does what thing are slightly different. The instructions that are available are different based on what processor you are in. Some of them have different codes for different things, but they all follow the same general concept. data stored in memory, instructions stored in memory, and the CPU fetches the instruction from memory, fetches any data that instruction needs from memory, carries out the instruction by activating a special circuit in the CPU, and then goes to the next instruction. In fact, the CPU is just constantly running through this really quick fetch, decode, execute, fetch, decode, execute, fetch an instruction, figure out what to do based on it, carry out the operations or activate the machinery inside the CPU that carries out those actions, and then go to the next one. And that's simultaneously very useful knowledge to have, but it's also a little bit frightening, because if somebody can get just a few bits to change in your program, they can change the behavior of it. And in our case, we changed one single bit in one single memory cell, and we completely eliminated the need to have that password to get to the presidential lunch codes. And that's kind of a fake example. If you want to build a program that has security, you'd have to take a few more measures to keep people from reading the password right out of the file. You'd have to take some additional precautions to make sure that comparison, but ultimately anything that has a comparison where it's saying let somebody in or keep them out, there has to be part of the program that makes that decision of let them in or keep them out. And since that's just bytes in memory, if you can find that part, you can bypass it. And they might build in other parts that look at that place in memory, and if that's changed, then they keep you out. There's a whole complicated way of trying to make it so you make it as difficult as possible, but really from the CPU's point of view, it becomes incredibly challenging to keep a talented programmer, hacker. And I don't want to use the word hacker as to mean that it's somebody doing something bad, because that's not really the original meaning of that word. A hacker is somebody who will kind of hack at something at this low level and work at it and work at it and work at it and understand it and be able to do things with it. And one of the things that we're not going to do any more of this in class except with our own programs. And one of the things that I would do is it's important that once you know this stuff and you know how to do it, use those powers for good. And there are cases where understanding this low-level nature of the computer can allow you to solve problems that you otherwise couldn't solve. And one quick story about that is at work, at my business, we make these little motion sensing, inertial motion sensing products. Here's one that I happen to have sitting here. This is one of our wireless units outside of its case. But on this, there's a little tiny microcontroller that has, right there's a processor and memory and everything all inside that one chip. And it works just like any other computer works, because that's how they all work. But the idea behind where this knowledge can be useful is the company that makes the compiler for this chip, they have a bug in their floating point library, meaning that when they created their compiler, the thing that generates this code like this, they have a case where you can take a really tiny floating point number and another really tiny floating point number, and you multiply them together. Well, a small number times a small number should give you a small number, but there's a certain case where a small number times a small number will give you a great big number, a huge number. And we ran into that in our code that needs to run on our products. And so we contacted the company and told them that, hey, there's this bug in your compiler. It's potentially dangerous or catastrophic. You really need to fix it. And they closed the ticket and said, we were wrong. So we opened a new ticket and said, no, here's some sample code that shows that your compiler has this bug in it, and you really need to fix it. And they said, well, we forwarded it to our compiler group to be fixed. And they closed the ticket and said, well, we're done with it here. The compiler group said, well, we'll maybe look at that for a new release. And that really bothered me, because these microcontrollers, could be used in like heart monitors or navigation systems for vehicles, or who knows what it could be used in, but it could be used in something that somebody's life depends on. And to me, the bug where you take a tiny number and a tiny number, multiply them, and get a huge number, is a very severe problem that needs to be addressed. And they basically didn't seem to take it seriously. They didn't seem to really care. They kept closing the tickets. We put in extra effort to even find where in the code the problem was and tell them how to fix it. And long story short, they never fixed it. So what we did is we loaded up their library kind of at this level, the kind of machine code instruction level. We figured out where the problem was in their library at the machine code instruction level, and we fixed it. And we fixed it by just changing part of the code. They had an off by 1 error in what's called the subnormal range of the floating point numbers, where it should have been less than or equal to, and they had less than. So we hacked their library and fixed it. And then now when we install that system on any computer, we go ahead and kind of hack their compiler every time. And then we even sent them the instructions for how to hack it themselves and said, this is a serious problem, needs to be fixed. Here's how you fix it in your library. You need to change this pattern that you find in memory to this other one, and then everything works. And they still haven't fixed it. So we've kind of given up on trying to help them make their product less dangerous, but all of our things that are built on that now work correctly because we knew how to hack their thing and fix it, which is what we did. Okay, so anyway, let's quickly go back to the presentation for just a second. And one thing, if you're going to use tools like this File Insight thing to edit the files, I did something a little bit dangerous there. I just went ahead and edited them live and then saved them. Usually what I would do is I'd make a copy. So I have a clean copy of it, the original, and then I'll make a copy and then I'll work on the copy and edit that and mess around in there. I wouldn't suggest that you start loading up, for example, pieces of Windows or other programs that you have and just start hacking and changing instructions like I did here. This was safe because those programs were kind of toy programs that I made just for this purpose. And the other thing is I'd suggest is to not randomly edit things without knowing what you're doing, without making a copy, and especially don't do things like that to parts of the operating system because you could make it so you have to reinstall the whole thing. So just be careful. But the thing is, this is how every program works. It works exactly like this. Just a bunch of memory, and then the instructions are in there, the data's in there, everything's in there with it. All right, let's switch back to quickly to the presentation. Okay, so I think at this point, or at least I hope at this point, I have proven to you that that is really the way the processor works. And we looked at the password program. Now, we're not going to be doing any more of that kind of hacking in the class, but knowing how the computer works is going to be important. This is a systems programming class. And so what I'm going to do now is I want to look at our first C language program. But what I'm going to do before we do that is I'm going to take a quick break, and then we're going to come back and we're going to do that. So I'm going to go and pause the recording, and then we will come back shortly and do part B, where we finish up what we're going to do in here, looking at our first C language program. So let's stop there. I'll be back shortly.